minute lecture series through Mali before. And I was approached by someone on the Mali board to consider doing a 6-session on hot springs and geothermal energy. And I agreed to do that. I'm very honored to have this chance to share with you how we look at hot water in so many different ways, from the geology of why the hot water exists to what life exists in hot water in Yellowstone and the fumaroles and the mud pots and even outside the park, and what animals survive because of hot water. And then we'll get into the social history of hot water, all the old resorts in Montana and the region, the beautiful old geothermal natatoriums and bathing pools, and then talk about how we're using hot water for energy, how hot water is used for space heating buildings and greenhouses and processing, and all the ways we're using hot water, even for making electricity from hot water, how we can use hot water to make power, and just exciting things happening in that technology. And then finally, we're going to end with an international session, just a tour of hot springs and hot springs resorts around the world, and talk about hot springs in Japan and Iceland and the Middle East or Central Europe and all over. So looking forward to your input about what you know about the hot springs, and looking at hot springs from all these different aspects over the next few weeks. And we're honored to have our first session kick off about the geology of hot springs with Dr. Rob Thomas from the University of Montana in Dillon. And I'll turn it over to Rob to introduce himself and talk about his session here. Thank you.
Great. Thank you, Jeff. Thank you all for attending, both out in cyber world and in person. Again, my name is Rob Thomas, and I'm a Regents Professor of Geology at the University of Montana Western in Dillon, entering my 30th year there. And my background with hot springs is mostly related to work that I've done in the Yellowstone region. I've co-authored both the Roadside Geology of Yellowstone Country book and the Roadside Geology of Montana book with Don Hyman, who's an emeritus professor here at the University of Montana. And so from those experiences, I hope to educate you today on how it is that hot springs work in 3 basic areas of our region: Western Montana, Eastern Montana, and Yellowstone National Park, because all 3 are different from one another. So we're going to start from the basics of how the Earth works, and we'll get to then the development of the kinds of geological structures that are required to produce the thermal features that we see in Western Montana, Eastern Montana, and finally Yellowstone Park. Okay, so with that, I will go ahead and move forward and just start from the beginning. So assuming that you have no background whatsoever, the planet started off as a molten ball. And we know this because the Earth is differentiated so that the heaviest elements are near the center of the Earth. So gravitational acceleration has resulted in differentiation of the Earth such that heavy things are towards the center and the lighter things are towards the margins. That means that it had to have been in a molten state for that to occur. So we have an iron and nickel core, for example, right? And the mantle is made out of iron and magnesium silicate minerals, which are a little lighter. And the crust is made out of sodium and calcium rich silicate minerals, which are even lighter yet. So the Earth is a big differentiated ball with heaviest elements towards the center. And it reflects this early molten phase at about 4.5 billion years ago. And as it cooled, it developed a crust, and that crust further cooled and developed 2 segments that we see over here called the lithosphere and the asthenosphere. The lithosphere is the rigid outer brittle part of the Earth. It contains the crust and upper mantle that are rigid, brittle rock. And underneath it, the asthenosphere is a hot Play-Doh-like layer. It's not liquid. It's maybe about 6% liquid. It's really a deformable solid. So it's you can think of it more like being like Play-Doh. But over long periods of time, it's capable of convecting or moving as a result of the high heat that exists there. These two are going to be most important. These two zones will be most important as we talk about hot springs. As you go at depth, the mantle of the Earth goes down until it hits the outer core, which is liquid, and then the inner core, which is solid, which are going to be less important in our story. Okay, so over the last 4.5 billion years, plates have come and gone as they form through plate tectonic processes, through accreting with one another and forming new plates, pulling apart from one another and forming new plates. And so what you're looking at in this slide are the plates that exist on the planet today. And the arrows show the movements in a general way that those plates have. And generally, there's about 20 of these lithospheric plates on the surface of the Earth. Again, the lithosphere being the rigid outer part of the Earth, which is crust and mantle, sitting on top of the Play-Doh-like layer, the asthenosphere. So these plates, 20 or so, depends on who you talk to. There are lumpers and splitters in geology, and so you can get up to 50 plus, but generally about 20 or so plates, and about 7 big mega plates on the surface of the Earth, all of which are shown here, and their movements. Of course, we live on the North American plate, and the boundary between the North American plate going to the west is with the Pacific plate, where it slides along the San Andreas Fault, and it collides with a little fragment of Pacific Ocean floor called the Juan de Fuca plate off the coast of Northern California, Oregon, and Washington. Okay, everybody good? All right. Plate boundaries are the most important thing about plate tectonics, because at the plate boundaries is where everything happens. So if you have the surface of the Earth covered by these moving plates, they can do 3 things. They can pull apart from one another, they can push into one another, or they can slide one past the other, right? Those are the only 3 motions that are possible. And so those are called convergent plate boundaries, divergent plate boundaries, and transform fault plate boundaries. Okay. That convergence, obvious, right? This is where the plates collide. Divergence, where they pull apart, and transform, where they slide one past the other. So why are these important? Well, because this is where everything is happening. Volcanism, earthquakes, mountain building, and the creation of topography, the formation of mineral deposits occur at these plate boundaries. And of course, from our perspective in hot springs, high heat flow, so that we generate an environment where water can be heated and come back to create a hot spring that we can sit in and contemplate plate tectonics. Everybody good? All right. Yes.
The New Madrid earthquake in
Yes.
the early 1800s, has that ever been explained in relation to plate tectonics? Because it's in the middle of the North American plate.
Yes. Yeah. So a lot of the plates that I showed you in this diagram, are subdivided into plates in the making. And so the Atlantic Ocean has been opening up, right, for about 250 million years or so. And along this spreading ridge, pushing the Eurasian plate, the African plate away from the North American and South American plates. As it moves to the west-southwest, it's coming up against the basin and range, which we're going to get into in detail, in the western part of the United States, which is pulling apart. That is driving a part of North America back against that arrow to the east. The collisional point between the two is the New Madrid Fault System along the Mississippi River corridor, which is an old weakness in the crust. And the two are colliding with one another there, and they generate some whopper earthquakes because they're compressional earthquakes. And so those big 8+ magnitude earthquakes that occurred in the 1800s in the New Madrid Fault System are a result of this. Does that explain it? Great. Okay. So again, these plate boundaries are crucial from our as a part of our hot spring story. All right. So speak of that. So let's go to the heat itself. What's driving these plates? What's generating heat? So the plates themselves are driven by convection. So just like a boiling pot of water on a stove, the heating element is causing that water to convect. So it's heating it. Things that are less hot are less dense and they rise. So as they rise towards the surface, what happens to them? They cool. And as they cool, they become more dense and they sink back down. And that creates a convective cell. So this is happening in the asthenosphere of the Earth, but it's happening at a very slow rate, because remember, the asthenosphere is a Play-Doh-like material. It's only about 6% liquid. So it's a deformable solid. It's not water on a stove. Okay. So that convection process is very slow. So convection in the asthenosphere drives the plates. And it's helped by two other processes. At the spreading ridges, here's a spreading ridge right here, the minute separating South America from Africa. Along that spreading ridge, there's push that is occurring. So the spreading ridge, as it pulls apart, is expanding up, and that's generating topography. That topography helps to push the rock away as it falls off that topography. So there's a certain amount of convection coming up, and then the overlying plates themselves are falling off that topography that's created at those spreading ridges. Okay, what we call ridge push. That's helping move the plate. Then the plate will subduct where it goes under something that is less dense than it, like a continent or a piece of ocean floor that's younger and warmer and less dense. And as it goes down, it's like a boat anchor sinking into the water. It pulls the rest of the plate with it as it goes down. Make sense? So at the spreading ridges, there's pushing happening, and where the plate goes down, there's pulling going on. So three things are happening to move plates: convection in the asthenosphere, creating movement, and then the overlying lithospheric plates are spreading and pushing away from the spreading ridges, and then they subduct or go back down into the mantle where, like a sinking anchor, they pull and help pull this motion along. Okay? Yes.
How was all this measured and named?
Yeah. A lot of work over a long period of time. But to shorten the whole thing up, the original proposal for plate tectonics was an idea called continental drift. And it was proposed by a German climatologist, Alfred Wegener. And he'd been working in ice regions and probably got the idea watching ice break up. and ice blocks collide and slide past one another and pull apart. And he came up with the idea that when you look, and actually it had been around for a long time, when you look at the surface of the earth, all the continents look like they fit back together again. And he created a word for that, Pangea, all lands, and made a proposal that the continents and the oceans are not static, that they have moved over time. And he created maps that showed this breakup of Pangea. What he didn't know, because this was in the early part of the last century now, was he didn't know much about the ocean floor. And so he envisioned somehow that continents moved, but the ocean floor did not, that the continent somehow plowed through ocean floor. And the geophysicists pounced on that and said, no, that's not possible physically. And he was the wrong person, the wrong place, at the wrong time. He was German. He made his proposal in 1919. He published The Origin of Continents and Oceans. And being German in 1919 was not a good thing. So, and then he made a third error. He went to Texas and gave his first talks in the United States on this idea of continental drift. And the Texas geologists were about oil. And they couldn't see how this idea of continental drift was going to help them find oil. And so he got savaged and he never came back, and he fell into a crevasse in Greenland and died. And that's the tragic end of the story of Alfred Wegener. Now, the Second World War came along, and we needed to know about the North Atlantic Ocean because of U-boats. So they started, the Navy started using sonar to map the Northern Atlantic Ocean floor. And they were like, there's big mountain ranges on the ocean floor in the North Atlantic. Everyone thought that the ocean floors were flat and featureless, had been there since the beginning of time. And that then translated after the war into work by folks at Scripps and Woods Hole Institutes of Oceanography to remap. They were given the technology by the government, but not the maps. And so they went and remapped it all. And out of that came plate tectonics in the 1950s, which was the idea that all of the surface of the earth is moving, not just the continents. That's how it differs from Alfred Wegener's continental drift. Okay, that's a long, that's the long story, but hopefully that helps. Yes, there's one more question. Sure, go ahead.
The last one I'll ask until it's over. What does the word asthenosphere mean? I mean, I know where it is, but the derivation of the word.
Yeah. Well, lithos is rock. Honestly, I don't really know the origin of astheno. It must, it's, you can Google it on your phone, but it likely has something to do with plasticity of that layer, in contrast to lithos, rock, right? So you have the rock sphere and you have this mushy sphere. But what the exact translation is of this astheno, I don't have the top of my head. Okay, and then lastly, the internal part of the earth also contains plumes of material that are stationary. Those are called hotspots. And hotspots are seemingly unrelated to plate tectonics, right? They stay stationary, the plates move over them, and like moving your hand over a candle, it leaves a track of itself as it burns through the overlying moving plate. Okay. Hawaii is one of the best examples of this, but so is Yellowstone. So it'll come back here momentarily. Whoops. So here we go. There's the 120 million years in a couple of minutes. Okay. So convection in the asthenosphere then driving these plates apart, being helped in this case by ridge push as well. Okay. So how about that internal heat? So remember, the early Earth was a molten ball, and it was a molten ball because it formed by the collision of particles in the nebular cloud as our solar system was forming. So as these planetesimal pieces are accreting with one another, they're generating a lot of heat. And so the early Earth is molten, and there's primordial heat remaining from the Earth's formation. Okay. But that heat is not enough to account for the heat in the interior of the Earth. There has to be another source of heat. Lord Kelvin figured out this, right? Because he tried to calculate the age of the Earth using a process of taking primordial heat to the point of the geothermal gradient that we have today on Earth to back calculate how old the Earth is. How long did it take to cool from a molten state to its present state, in other words? And his calculations were off by a lot. He saw the world as being about 100 million years old, and in fact, it's 4.5 billion years old. So Kelvin, who was a brilliant physicist, made an error. But that's okay. We all make errors. Even Lord Kelvin, who was notoriously an arrogant man. So the interior of the Earth has a gradient to the temperature. In other words, it gets hotter as you go deeper. So we know this from mines, right? So the Butte mines, the Butte miners, it would be down at the 5,000 foot level at 120 degrees Fahrenheit. And, as the lore goes, the school kids would come in, the dead of winter to watch them come up out of the mines, right? Because they would be covered in sweat, and it would be 40 degrees below zero, and they would hit that and just go up in a puff of smoke, right? As they hit the cold air. So it gets hotter as you go deeper, and that's called the geothermal gradient. And some of the heat source is this primordial heat, but a lot of it is radiogenic isotopes. In other words, there are isotopes of elements, meaning elements that lose particles from the nucleus of the atom, and they generate heat in the process of doing that, right? Like uranium. Okay, everybody good? And that's what Kelvin messed up. Kelvin didn't understand, radiogenic isotopes and the addition of that heat into the system, which makes the Earth hotter than it would be if it were just primordial heat cooling off to the present. Everybody good? All right. So the average gradient, we'll just stick with the Fahrenheit. I'll just say about 80 degrees Fahrenheit per mile. And so, to give you some feeling for that, water at 3 miles would be about 240 degrees Fahrenheit. And then as it comes back to the surface, it loses heat, right, to the cool rock that it encounters. So that's not the temperature of most of it at Lolo Hot Springs, right? Or any of the other hot springs that you occupy. So there's a temperature change in that water as it comes back to the surface. When we look at a map of the gradient and the surface heat flow, so this map on the lower right is a map of the surface heat flow for the planet. What do you notice? You notice that the areas that are hottest, shown in red, are associated with the plate boundaries, right? You can see the plates by the heat flow, by the surface heat flow, especially the divergent plate boundaries, the places that are spreading and separating continents and making oceans. Everybody good? Okay. All right. So let's hone in on the US. So here's a map of surface heat flow in the continental United States. And what part of the United States is most tectonically active? The West, right? So you can see very clearly the Western United States is great. Iowa, I'm sorry, Jeff, not so great. If you like hot springs. I'm sure it's great in many ways, corn, but not for hot springs. And so the Western US has a high surface heat flow because of the tectonism. Now, the map that I showed you earlier of plates did not show a plate boundary here. This is an incipient plate boundary. So this is one in the making, right? The Great Basin of the Western United States. Of course, what's that line along the edge of California? That's the San Andreas Fault System. This is the Cascade volcanic chain going up through Northern California, Oregon, and Washington. And this little finger right there is the Rio Grande Rift. And that rift means pull apart. So that's another one of these divergent plate boundaries in the making. Right, it goes through Albuquerque, New Mexico. And there's nothing, yeah. Yeah, I'm not going to even go down that path. All right, so then earthquake probabilities. So when you look at a map of earthquake probabilities, you can see it mimics the map of heat flow at the surface for the continental United States. So the activity is in the west. And the reason why it's important for me to show you, and there's your question, there's the New Madrid fault system, right? And it's because this is moving that way and this is moving that way. And the point of collision is right here. So these earthquake probabilities are important to show as a part of all this, because as we'll find out, earthquake fault lines are important avenues for water percolation down into the subsurface at depth where it can be heated and then rising back to the surface where it can be enjoyed. Make sense? All right. So where are the thermal springs in the continental United States? They're exactly where all the other maps I showed you show activity of surface of plate tectonics and earthquake activity and surface heat flow. Make sense? Okay. All right. And again, there's poor Iowa. Growing corn, not doing much else. Okay. So, in a nutshell, the geological conditions that are required to get these thermal features are a water resource, a heat source, and a good plumbing system. Simple as that. So groundwater can be that water source, or surface water that's flowing to depth could be that source of water. And depth meaning ballpark about 3 miles or so. Okay. Typically, groundwater is not much below 5 miles depth. Why? Because there's so much pressure on rock at that depth that the pore spaces are collapsed that would hold groundwater. Make sense? So you lose your porosity and permeability with depth. So you get below 5 miles, depending on the rock type and the environment, you start losing your ability to store water in the subsurface. Okay, heat source. We already talked about that. The Earth's geothermal gradient, right? About 80 degrees Fahrenheit per mile, and then a plumbing system. And we talked about that. Faults are a great plumbing system into the subsurface, but the other are joints. Joints are fractures in the rock that don't have movement on them. And that can happen in igneous rocks, where a magma, a liquid rock, cools, and when it cools, it contracts. And when it contracts, it cracks, and it creates joints or fractures in the rock that don't have movement on them. They're not a fault, but they are conduits into the subsurface. And so you have a close by example. This is Lolo Hot Springs. So you have granite of the Lolo batholith up there at Lolo Hot Springs. About 50 million years ago, it crystallized When it crystallized, it fractured as it contracted, making joints or cracks in the rock. Okay. Some later structure and extension of the area has helped to create more cracks. And those are conduits then for rain and snow to percolate down into the subsurface, be heated, and then driven up other cracks to the surface to create the hot spring. Everybody good? All right. Here is a fault example, Jackson's Hot Springs over in my country, down in the Big Hole. These are faults in the West Pioneer Mountains. So rain and snow falling in the West Pioneer Mountains percolates down these faults. They hit another one of these faults where they rise up to the surface. And they also have some hydraulic head to them, right? There's a column of water that's pushing down on this water that then can come up. So it's heated, it's less dense, so it can rise, and it's being pushed by a hydraulic head, by the water behind it. Everybody good? And that's Elkhorn Hot Springs, a little closer to Dillon. And it's also a fault-controlled hot springs. All right. So how do we have these fault-controlled hot springs in Western Montana? So bear with me. I'm going to walk you through the whole last 50 million years of Earth history to get you to the modern, to where we can explain these fractures, these faults and fractures that create hot springs. All right, we got to go all the way back to the time of dinosaurs. So let's take ourselves back to, say, 120 million years ago, during a period of time called the Cretaceous. And you had in Montana an interior seaway that connected up the Arctic Ocean up here with the Gulf of Mexico down here. And here's Montana, and dinosaurs were living along this coastal margin, so that the egg sites like at Shoto and so on, these are proximal. They're basically floodplains of river systems draining the mountains headed into what we call the Western Interior Seaway. Okay, here it is in cross section. And these mountains that were in the western part of Montana were from convergence. So this is from two plates colliding with one another, not pulling apart. So at this point in time, Montana is a collisional plate boundary. And the collision was between an ocean floor piece called the Farallon Plate. You can just think of it as the Pacific Ocean floor at the time, and the continent of North America. And the collisional zone was around what is today Spokane, Washington. So it was ocean from Spokane west at this time, about 100 million years ago, we'll just say, ballpark. Okay, are we good? All right. This squeeze took all the rock that had previously existed and piled it up into a big pile of folded and faulted rock that got compressed, kind of like a bulldozer plowing in and plowing it up into a big pile. Okay? That's important, because what happens when you back off of that pile? It falls apart. Okay? So the bulldozer was plowing in up until about 50 million years ago. And when it started to back away, the rock pile collapsed. Why did it back away? Because we started adding pieces of continental material here to the western margin of North America, and the subduction zone kept moving westward. It's currently hundreds of miles off the shore of Washington State. So the bulldozer was backing off with each fragment of land that got added on. Okay? So what happened is Western Montana started to extend about 50 million years ago. This is the beginning of the Mission and the Flathead and the Bitterroot and the Big Hole and the Deer Lodge and several other valleys. They all started forming about 50 million years ago. It's this big welt of compressed rock from the earlier time, the time of dinosaurs, started to fall apart and extend. Okay? Okay. That crustal thinning, whoops, looks like this. So as it fell apart, the lithosphere, the rock sphere, is brittle. So what happens to it? It breaks. And it breaks into blocks that drop and blocks that rise relative to that basin and range topography. There it is. Everybody good? Here, I can do it again. I think. All starting about 50 million years ago. The zone at which this happened, you can see in the graph on the right. So there's a zone, we call it the rift zone or the zone of extension throughout western Montana, which is this area of collapse that started about 50 million years ago in formations of basins and ranges. All right. Notice that each of these ranges are bound by vertical cracks that go deep into the earth. Why is that important? Water percolating down, heating up, coming back. All right. These faults from 50 million years ago are not part of your equation of your modern hot springs. Okay. They're dead and gone, and they're not the cause of the hot water coming to the surface. We've got a lot more extension to go. So hold on. Okay. 17 million years ago, the San Andreas Fault starts forming because a spreading ridge off the coast of the western margin of North America gets subducted. And the Fairlawn Plate, this isn't working real well, that was subducting, it breaks off and falls into the mantle. And all that creates upwelling currents that are doing this, convecting. And remember, convection drives plates apart. And so starting about 17 million years ago to the south of the Snake River Plain, the Great Basin went from compressional to extensional. It started pulling apart, forming basins and ranges, just like this. Everybody okay? Yes. So south of us, basin and range topography starts forming 17 million years ago, largely because the Fairlawn Plate broke off and fell into the mantle. And we also subducted the spreading ridge and created the San Andreas Fault. So that released compression on the western edge of North America. Okay. Now, to the north, things are a little different. Yellowstone emerged in northern Nevada at the same time. There it is. So at the three corners between Nevada, Oregon, and Idaho, 17 million years ago, a hotspot emerged through the continent of North America, which was moving to the southwest over it at a rate of about a couple of centimeters per year, about the rate at which your toenails grow. Okay. Now, when it did, it domed everything up around it. Well, what is the lithosphere? Rock. Lithos, rock sphere. It's brittle rock. If you dome it up, what happens to it? Like a rising loaf of bread, it cracks. So as it rose up, it cracked and it extended. It pulled apart, right? Just like crust on the top of a bread that's rising. So it extended, it broke, and it created basins and ranges that were northeast trending in Montana, and that started the Missouri River. The Missouri River started flowing through Montana 17 million years ago off the Yellowstone thermal bulge. How do we know that? Because of this. That is a tower of ash down by Dillon. That was a very bad day 10 million years ago. It was a wall of water and ash from a caldera eruption of the Yellowstone hotspot that was located at the time about what is today Twin Falls, Idaho. And it went down the ancestral Missouri River drainage into Montana, and it left a 120-foot thick pile of ash in the river. It completely covered the river bottom from side to side in its maximum over 100 feet of ash. Unbelievable. You got to go down and see these. They're in the Black-tailed Deer Valley of Southwest Montana. It should be a geoheritage. It should be a world geoheritage site. Yes, it is. All right. And here's another piece of it. My student here, Isaac, is standing on top of the ancestral Missouri River 17 million years ago to about, in this case, 6 million years ago, because what he's standing on is a flow of basalt. And that flow of basalt has been dated to 6 million years and has been traced to its vent, which is near Rexburg, Idaho. That means that every mountain range between Rexburg and Dillon, this is in the Sweetwater Range, east of Dillon, that's the Tobacco Roots over here. There's the Greenhorn Range over here. Virginia City is right in here. Okay. None of that topography was there. It's 6 million years ago. The older I get, the younger the extension of Southwest Montana and Western Montana gets. When I was a student here, the word was that extension started 50 million years ago, and every valley that you see is 50 million years old. Had been accumulating sediment for 50 million years. The Missoula Valley, the Bitterroot Valley, the Flathead Valley, the Deer Lodge Valley, the Big Hole Valley, all of them. That's nonsense. Okay? That's nonsense. We put it all together by studying the deposits that went off the thermal bulge down the Missouri River. It allowed us to time when the mountains formed because they couldn't have been there for that river to flow through there. And it went all the way to Hudson's Bay, where there's a deposit of that ash. We call it You Bet Your Ash. And it made it all the way to Hudson's Bay, and it's in deltaic deposits in Hudson's Bay, Canada. We've got this thing nailed. Okay. And this basalt flow was a crucial piece of the puzzle because you can trace basalt flows to their origins and see where they came from. In the last time I looked, basalt flows don't go on up and over mountains, right? It would have had to go over the Beaverhead Mountains, over the Tendoy Mountains, over the Blacktail Mountains, over the Sweetwater Mountains. Didn't do that. They didn't exist. A story for another day. All right. So here's the hot spot, and the plate is moving to the southwest over that hot spot. Remember, the hot spot's stationary. So the plate at the outbreak point down in here was back here 17 million years ago. Okay. So it's been moving this way, the plate, and the hot spot then is now emergent here at Yellowstone National Park. And as it does so, it domes up the rock around it. So the Beartooth Mountains and the Absaroka Mountains of Wyoming, they are all domed up out in front of the Yellowstone thermal bulge. Okay? In other words, they're high topographically. The Beartooths are 12,000 feet. The Absarokas are 10,000 feet and change. It's all elevated. As the plate moves over the hot spot, the elevation is not able to be held up any longer by that big thermal mass in the subsurface, the big magma chamber. It collapses. And what you see are a bunch of northwest trending faults shown as red lines here that are the collapse features as the hot spot relatively moved to the northeast, meaning the plate moved to the southwest over it. Y'all with me? So as the plate passes over the candle, the area behind where it passed falls apart. It extends and falls down. That's when the mountains formed. That chopped up the old ancestral Missouri River deposits and made them exposed in the mountains where we can study them today. And there they are. Okay. And they're older back here in Idaho, and they get younger as you come up closer to the modern, or, the modern location of the hotspot. So these collapsed first, then these, then these, then these, then these, and these. Okay. In Southwest Montana, the age of the faults are about 4.5 million years. That means the continental divide that you know today formed 4.5 million years ago. That is yesterday geologically. Okay. It's scary. It's scary. Think about it. Butte, Montana, Our Lady rising into the heavens, Butte dropping into the pits of hell. Along the continental fault, an active northwest trending extensional fault. If it ruptures, as did Hebgen Lake, Quake Lake earthquake in 1959 at 7.5 magnitude, Lord help the people of Butte, Montana. I won't go into the details because it's being recorded and I'll get into trouble. But it's not a good situation. And that's true of all of Western Montana. One thing I like to always point out, just to scare people a little bit, because it's always fun to predict and scare, is there are big tension cracks on top of the Mission Range above Big Fork. They are big fractures from the mountain range failing as a rockfall. All right. We know from digging trenches across the Mission Fault that it ruptures with 7.5 magnitude earthquakes, and last did so about 1,300 years ago. If that happens, I can envision a slab of rock coming off the Mission Range, hitting Flathead Lake, sending a tsunami wave across the lake and taking Polson off the map. Okay, those are your active faults. So enjoy those hot springs because they come at a price. We have an incredible earthquake hazard in Western Montana that is largely overlooked. And this is how it got there. It's this blasted hotspot, creating these active young faults around it and reactivating older faults that have been going on for 50 million years, like the Mission. Okay. All right. The map on the bottom right there just shows, here are the flow paths in a Google Earth image of the ancestral Missouri River here through Dillon. Here's through the Ruby region. And then all these mountain ranges weren't there. So there's the Continental Divide right there. There's the Continental Divide right there. The Tendoy Mountains, the Mission Hills, the Blacktail Mountains, the Sweetwater Mountains, the northern end of the Ruby Range, and the Tobacco Root Mountains, all of which have come up in the last 4.5 million years. Yes.
As a science teacher, I have some background in this subject, and I'm aware of the fairly high earthquake potential. And I have tried to find out if there's anybody in Missoula that knows how to anchor houses to their foundations, and do the power companies have the technical knowledge to put these earthquake shut-off valves on my own line, or maybe on their lines. And the insurance companies, it's like nobody in insurance companies or the power company is very much aware of the high earthquake potential we have here. And I find it mind-boggling. I think it's highly irresponsible.
Yeah, we have one state seismologist, Mike Stickney.
I know. Yeah.
Mike's great. He's the best state seismologist in the United States, but he's not got a big team.
Yeah. So I think the power structures are not aware, like geologists are, of the earthquake potential here as far as wanting to,
Yes.
to prepare us. I mean, over in Oregon, my daughter has people that know how to anchor a house to the foundation. I see on YouTube all these shut-off valves that'll turn the valve, the natural gas off, you
Yes.
know, when there's very much of a shake. And around here, it's like nobody knows anything about that.
Yep.
I find it extremely disturbing.
Yes, I understand. Yeah, I mean, Mount Sentinel is a big active normal fault. I could probably go outside and throw a rock and hit it. How much do you hear that discussed? Okay, so earthquakes occur on these northwest trending normal faults. In southwest Montana, there is the fault scarp from the 1959 Hebgen Lake fault. There's a human being for scale. So what happens is that movement build up stress and boom, releases the energy, movement along the fault, creating a fault scarp, just like you see here. Okay, let's do that again just for fun. And because there's movement, that's generating porosity and permeability along that fault plane for water to percolate down and up. So the hot springs, the thermal features are associated with these faults. Okay. All right. So an example, Jackson Hot Springs. So the surface water we think penetrates to about 2 miles on an active extensional fault. It's hard to see on this map. Jackson is right here, but there's an extensional fault right here, and that's where the water emerges, is out that fault. The water gets in up here in the West Pioneers as snow melt and rainwater. It percolates down a bunch of other faults, hits the fault, and is heated as it goes to depth to a temperature of about 260 degrees Fahrenheit. And then it gets that hot at that depth because the geothermal gradient is higher in southwest Montana because the lithosphere is thinner. So it's a little higher number than the average number. Okay. So as it heats up, then it rises to the surface. It also has hydraulic head helping to push it to the surface, and it comes out as Jackson Hot Springs, which is right here. The water chemistry reflects the rocks that are encountered by that hot water. So you don't have a sulfurous smell at Jackson Hot Springs because it's not encountering sulfur in the minerals of the rock that it's traveling through. The rock it travels through is mostly quartzite, which is made out of quartz, silicon, and oxygen. No source of sulfur. Make sense? Okay. It picks up some calcium and a few other elements depending on some other types of rocks that it encounters on its way on this journey. But the chemistry of these thermal features very much reflect the rocks that they migrate through, that the hot water migrates through. And then, of course, Sacagawea directed William Clark on the return trip to Jackson Hot Springs in 1806. They landed there on July 7th of 1806, and they had broken or lost their thermometer by that time, and so they boiled meat to get a handle on what they thought the temperature was. And they also would take their finger and put it in there and see how long they could keep their finger in the water. And they were testing the other hot springs in similar ways. So in the journals, there's a lot of comparison between Lolo Hot Springs and Jackson Hot Springs because of their physical proximity to one another. Okay, Eastern Montana. So there are hot springs in eastern Montana, and you're going to hear all about them from Jeff. And they're there because the Earth has a geothermal gradient. It gets hotter as you go down at depth. So if you've got what it lacks, remember those three things that you need a source of water, right? You need a source of heat, and you need a conduit to get a thermal feature. What's missing in eastern Montana? The conduit, except oil and gas wells. Oil and gas wells. So this is a map that shows oil and gas wells in Montana. Okay. And not all of them. These are ones that they took and measured the borehole depth temperatures. So they went down to the bottom of that hole and they measured the temperature of the water at the bottom of that hole. And they're colored different colors, which don't show up real good, but you can see that they're really red up here in northeastern Montana. That means they're higher temperature there. And that means that the wells are deeper. Because the oil and gas that they're getting in that part of Montana is out of a unit called the Madison limestone, which is a old limestone. It's in blue here in this cross section from the Fort Peck area. And it is down there anywhere between 5,500 to 7,500 feet below the surface. So you take the geothermal gradient, you go down 7,000 feet, you get some pretty hot water, right? Now, one of the problems with a lot of that water is it's real briny, right? It's full of salts, and it's full of gas as well, right? So the one place that I wanted to feature is a fairly well-known hot springs near Malta, in the Malta area, east of Malta, called Sleeping Buffalo Hot Springs. And this is a well that was drilled down to 3,200 feet, and the water comes out at the surface with at 495 psi and carries a temperature of 108 degrees. And so that well generated hot springs, and it's got a long history to it. Jeff might talk about it later in class, but it involved Roosevelt era works project and helping to remove the gas out of the water so that they could make it a hot springs. You could light it on fire in the day. It had so much gas associated with the water. So there's a lot of potential for thermal features in eastern Montana, and maybe more importantly, there's a lot of potential for geothermal energy in eastern Montana because we got a lot of heat and we got a lot of wells to access it. So that's something to consider, right? Something for those oil and gas company guys to do going forward. Make energy with geothermal. It's already there. Ready to rock and roll. Okay. So you can see in this cross-sectional view, eastern Montana just lacks the avenues for that water to get to the surface, right? There's no fractures and faults and so on like I showed you in western Montana. It's the plains. It's Iowa. Not much happening out there. But there's still a geothermal gradient. So if you got a hole in the ground that was created by humans, you can get this. Sleeping Buffalo Hot Springs. All right. And last, Yellowstone. So we don't have nearly enough time, right, to go over everything that's cool about Yellowstone and its thermal systems. The thermal systems are incredibly diverse, incredibly complex. There are people that are devoted to them. I teach for Yellowstone Forever, used to be the Yellowstone Association in the park. I've done that for decades. We call them geyser geezers. These are typically people with not much else to do, who know every little detail about every hot spring, every geyser, every fumarole, every mud pot. They know how frequently they go off. They know their temperatures, and they love to catch you being wrong. So I avoid the geyser geysers by talking about why the hot springs are there rather than the details of how often it goes off. All right, so why is it there? Well, Yellowstone is a continental hotspot. It's a stationary plume of magma that goes, and magma is a loose term. This is something that is just a little hotter rock than the rock around it. It's still, don't think about it as being this big pipe of liquid going into the subsurface. These diagrams, and this one's out of my book with Bill Fritz, they are misleading because you put them in bright orange and red, and people are like, ah, depth at depth, right? No, it's only a percent liquid. It's really a mushy solid at depth. And we see it geophysically because when you pass waves down into the interior of the earth, they slow up when they hit something that's hot and mushy. And that creates an outline that shows us, oh, here's a zone that's hot and mushy. Make sense? So there it is. This was created by Bob Smith at the University of Utah. It was a National Geographic, and it's a little teeny bit marketing oriented because there's a lot of debate on how far this thing goes. It's being shown here at 500 plus kilometers below the surface. And there's some people that don't think that think it's much shallower, but I won't go into that debate. That's another talk for another day. But so let's just assume that it is a deep mantle plume and it goes down to 500, 600 kilometers below the surface. The plate's been moving in a southwesterly direction over it, creating caldera after caldera after caldera after caldera to the current place where it's located in Yellowstone National Park. You can see that it's been modeled to dip to the northwest right underneath Dillon. So I like to scare my students. The hot spot is right under their feet, but 600 kilometers below their feet. All right. So then honing in on the park itself, you can see the outline of the caldera. The caldera is number 3 is the most recent, and that's the most active one. And so number 3 is right here. And so that outline there is what's called the Yellowstone caldera. And that's the one that formed 639,000 years ago. So that's the most recent caldera that formed in the park. And it's big, 45 miles long, 29 miles wide. Okay. It is 1,000 times larger than Mount St. Helens. Think about that. 1,000 times larger. You could take and put 1,000 Mount St. Helenses inside of the Yellowstone caldera, which erupted 639,000 years ago to form that caldera. That was a bad day. Now, is it going to happen again? Yes. Is it going to happen in your lifetime? Likely no. You're much more likely to get killed walking on the streets of Missoula than you are to be dying in an eruption of the hotspot. Just slipping in the bathtub is a much higher probability. So nothing to worry about, but fun to talk about. Okay, how does it work? So the magma chamber is gigantic in the subsurface. So 50 by 25 miles is the size of the magma chamber. It's 5 miles thick. Okay. And it's only 5 miles deep below the caldera. Okay. This is the top of that big red thing I showed in the other diagram going down at depth. All right. So that big red thing going down at depth is just a zone of kind of mushy rock. But there's an actual magma chamber, and that magma chamber is about 5 miles below the surface. And there it is. Everybody good? All right. That makes the geothermal gradient in Yellowstone off the charts high, because it has this gigantic source of heat that is so close to the surface. Make sense? All right. But we still have to have what? Water and what? Plumbing system. Very good. So we got to get those. We got a source of heat. This gigantic magma chamber that's not very deep below the surface, but we got to get those other two. Here's how it happens. So here's the magma chamber in cartoon form. As it rises up, the overlying brittle rock is like the loaf of bread expanding up. What happens to it? It cracks. Those cracks become avenues for the escape of gas and fluid, okay, which is under pressure. And as it does, it's like taking a bottle of Coke that you've shooken up and just slowly uncorking that thing. And the more it uncorks, the more it comes out. And the more it comes out, the faster it comes out. And it creates this multiple gigantic columns of ash, which are just crystallized droplets of liquid. They're not crystallized, they're glass. So frozen liquid, if you will. Okay, and gas, and some pieces of rock, and some crystals that were in the magma chamber. And all that stuff blows into the atmosphere as high as the stratosphere. Okay, so higher than Mount Everest. And all that material in that column, what's called a Planaean column, cannot hold itself up, and it descends upon itself, and it squirts out in every direction when it hits the ground. It goes down all the river valleys, is a screaming flow going hundreds of miles an hour, carrying thousands of degrees of temperature, called a pyroclastic flow, fire rock flow. Everybody with me? Okay, those are bad. Okay, you can envision, a horse in Southwest Montana eating the grass, and the shock wave would have hit it before anything else and blown it to bits, and then incinerated the particles before anything got buried over the top of it. We don't find fossils in these pyroclastic flows. Okay, all right. Once you've blown all that stuff out, the top of the magma chamber is vacant. And it all falls in like Crater Lake. It's a caldera. It's not a blowing out. It's a collapsing in. Everybody with me? All right. And then as it collapses in, it creates more fractures. Okay, what are those in our formula for getting a thermal feature? Conduits, right? Plumbing system. A way to get water down, a way to get water back. Got it? All right. And then some of them get covered over by the rhyolite and basalt flows that come out to fill up the caldera over time. And some of those don't stand a chance actually against that hot water, and they get pulverized as the water migrates up through them. That's why the Grand Canyon of the Yellowstone is where it is. That's a rhyolite flow that went over a thermal basin. All that hot water percolate up through the rhyolite flow just made it into clay, altered it to clay. So the river cuts a big canyon right there because the rock's soft. Make sense? Okay, way too much to talk about. Again, it's a whole nother class. But fun. Okay, so the hot springs. So here's a map that shows the hot springs, and the colors, not hot springs, thermal features, and the colors that you're looking at are chemistries. So here's Mammoth, and that's limestone that's forming the terraces, right? The travertine terraces at Mammoth Hot Springs. These green things down in here are sinter deposits. That's silica that's in solution in the upper, middle, and lower geyser basins within the park, and etc. And so here's the outline of the caldera. And you can see that thermal features occur both in the caldera and outside of the caldera. Okay, a lot of these that are outside of the caldera are from faults that radiate away from the caldera. So Mammoth, for example, comes from hot water that has been traced through the Norris Geyser Basin along the edge of the Gallatin Range here, and then it follows faults downhill where it then pops out at the surface to create Mammoth Hot Springs. And it's all been traced. We know exactly where that water came from. Okay. All right. So here it is, water percolating down, hitting hot material. It does not hit the magma. Okay. It's only hitting hot rock that is well above the magma. All these thermal features are in the top 600 feet or so of rock. The magma is much further down. That's a misconception that people have, that the water percolates down and hits magma. It's not. It's hitting hot rock that's heated by the magma. Okay. And then it gets heated and it rises back up and it creates the various features. Hot springs, geysers, fumaroles, and mud pots. Differences: hot springs. The water comes out of the surface, creates a pool. Geyser, the water can't make it out onto the surface to make a pool because of constrictions. So then it creates a buildup of water weight and gas, and it violently erupts out and squirts out of the ground and creates a geyser. Fumaroles are areas where you're above the groundwater table enough that what's mostly coming out is gas. They make that sound, right? And then mud pots. And the mud pots occur in places where the hot water goes through rock that's full of a mineral called feldspar, which is altered easily to clay, mud. So if there's a lot of clay, you get a mud pot. And the mud pots change over the year, right? So that when there's more water in the early part of the summer, spring and summer, the mud pots are more fluid, and as you go on, they become less fluid through the remainder of the year, the tourist year, I'll call it. Okay. So 3 kinds of hot springs, thermal features in Montana. Those in Western Montana, plain and simple, are from extension of the crust, creating fractures, cracks, faults, extensional faults that allow water to penetrate down at depth, be heated, come back to the surface as a thermal feature, a hot springs, a warm spring. Are we good? Eastern Montana, there's a geothermal gradient as well, but the conduits are not there naturally. So they instead come up human-made conduits, wells. And last, Yellowstone, the world's largest explosive volcano. Sitting on top of it is a thin crust of rock that's very hot from that magma chamber in the subsurface and full of fractures from the formation of the caldera itself. Water percolates down through there, groundwater is down in there, and that gets heated and it comes back as the various thermal features that we see in the park. Okay. It's a much higher geothermal gradient than Western Montana and the hot springs that we see in Western Montana, because that magma source is so close to the surface. Again, about 5 miles down. Are we good? All right. What I want to leave you with is that I can explain these and we can go through this geology and it's really interesting, but there's a, I don't know, there's a beauty to them in many different ways, including the knowledge of them. I've had people ask me all of my career, does understanding how the mountains form take the beauty of them away from you? And I'm like, what kind of a dumb question is that? Are you kidding? They just enhance the ways in which I can learn more and more and more and more about those mountains. and makes them that much more interesting. And I think that they do a great job. My friend Hank Hansler from the park does a great job in this film of getting this across. So this is just about 6 minutes worth.
There is a lot of discussion nowadays about why Yellowstone was made the world's first national park. Put yourself back in 1865, and you come into this area. Is the remoteness what is unique? No. When you found a town in 1865 in the Rocky Mountains, that was unique. Were the wildlife? No, you lived off the wildlife. Was it spectacular scenery? No, Rocky Mountain area was known for its scenery. What was unique in the 1860s, 1870s to the people who came here were the thermal features. There's approximately 900 geysers worldwide, and we have over 500 of those in Yellowstone.
This is a geologic park, first and foremost. That's why it was set aside. And today it encompasses 2.2 million acres of pretty wild land. More geysers in this mile and a half or so than any place else in the world.
Yellowstone is a great place to see geology alive and in action daily. And we need to have places where people can experience these unique natural phenomena for themselves.
Wow! I live in Minnesota, and this is not something I see every day. So I enjoy coming out here just to see something different, something that's part of nature, and something that's a lot bigger than I am.
When you see boiling water shoot 150 feet into the air on its own accord, then you're like, wow, that is definitely something that we're just a small piece in this really cool world. A geyser is basically a hot spring that erupts. It acts like a pressure cooker, and so when that pressure is released, all the water underneath flashes the steam, pushes the water out into a geyser eruption. So it's basically like nature's natural fountain.
Every eruption is unique and beautiful in its own way. Geysers have their own unique personality. Some are very unpredictable, a few are predictable. Depending on the wind and the pressure of the water and how much recharge, you get different eruptions. Geysers are what we call mathematically chaotic systems. Slight variations in the amount of cold water coming in, the amount of heat coming up, a change in the plumbing system can give you dramatically different results. And what I enjoy seeing is not the reproducibility of geysers, but the infinite variety even within a single geyser.
We're lucky we can predict the 5 or 6 that we can. And that can vary from year to year, whether or not we can predict and maybe how big a window around them. I think it teaches us to respect natural systems that don't operate on our time frame.
Now, a geyser like Old Faithful has a name for a reason, and it is fairly faithful. It's a period between eruptions has lengthened from 60 minutes to about 90 minutes over the last 30 years. Will that continue? We don't know. Someday, may Old Faithful stop? Yes. But the main point of this national park is to let natural geologic processes go on without we as humans affecting them.
We preserve them not for what they can do for us in terms of something economic, but in terms of what they do for our hearts.
So the beauty in nature is in the learning. The beauty of nature is in the learning. And that is something that I hope that we as a species can internalize before it's too late. Thank you very much. Questions?
I happened to be caught by one of those geysers that went off in Yellowstone, and I expected that the water would be hot, and it was not. So why is that? If it's hot water that's under pressure.
I'm sorry. That I don't know exactly the case, where you were, which geyser and so on, but the exchange of heat from that water into the atmosphere is very rapid. So the water that hits you might have just simply been cooled off, yes. So it was probably already dramatically had lost its heat by the time it's coming down. If you look at, say the Upper Geyser Basin by Old Faithful, and how close the boardwalks are to some features that are known to produce some pretty big geyser eruptions, you wonder, was somebody thinking carefully when they built the boardwalk? And the reason why there's that close proximity is because they're pretty predictable in terms of what's going to happen, and what you're mostly hit with is the mist is coming back down, which is dramatically cooled.
Very hot.
Oh, yes. Yeah. So when they tell you to stay on the boardwalk, you stay on the boardwalk because, it's incredibly dangerous. The center is very thin in places, and, there are annual catastrophe, tragedies.
I've recently been reading up on Mount Rainier, and in one of its big eruptions, it lost, I think, over 1,500 feet of elevation. So I don't think it was on a magnitude equal to the caldera eruption of 600 and some thousand years ago, but it was still pretty big.
Yes.
And the pyroclastic flows went all the way to Tacoma and Seattle, 50, 60 miles away. And are there any Montana towns situated on top of pyroclastic flows, which is really not a good idea?
Yeah. So as the hotspot has progressed, as the plate has moved over the hotspot, we see several pyroclastic flows. They're called tuff. So one near Dillon is called the Kilgore Tuff. It doesn't make it to Dillon. It makes it south of Dillon. It's prominent in the Centennial Valley area. Another one is the Huckleberry Ridge Tuff. That's from the 2.1 million year eruption of the Yellowstone volcanic plateau volcanic field. And that one forms the what people call the Palisades along the Madison River. And it extends south of Ennis, to not make it all the way up to Ennis. That happened 2.1 million years ago. So the position of the caldera that produced that has changed some. And so the areas that would be problematic would be Jackson, Gardner, Livingston, perhaps. It's pretty far north, depending on the size of the caldera. But again, the probabilities are incredibly low. So if you go through the hierarchy of probable eruptive things to occur in Yellowstone, the much more likely things to occur, things like having a hydrothermal explosion crater form, like Mary Bay and Yellowstone Lake, Indian Pond. There are several examples of hydrothermal explosion craters. Their frequency is greater. So as a result, their probabilities of happening on our time scale are greater. Caldera forming eruptions, yes, you know, we have 3 data points. The one at 2.1, one at 1.3, and one at 639,000. All right, well, that translates into about a 600,000 year interval. But no statistician is going to feel very good about that. That's 3 data points to get an interval of 600,000 years. And the slop between that timing of repetitive caldera formation is such that it's not really relevant on our time scales. And then you have to add to it that the Yellowstone is moving into the hotspot's moving into a fundamentally new place. It has been moving through thinner lithosphere up to now, and it's about to hit a change to a much thicker lithosphere that it has to go through to make it to the surface. And some people think, like a blanket, it'll snuff it out. But who knows?
That's good news. Then if the lithosphere is thicker, that's heading toward the hot spot. Is that what you said?
Yeah, that's correct. So the lithosphere that's heading towards the hot spot is thicker. It's right on that edge right now.
Make it less likely to erupt then.
That is correct. Yeah. And again, the current caldera, Yellowstone caldera, the most recent, 639, has so many different kinds of things that can happen within it before a new caldera forming eruption would occur that talking about a new caldera forming eruption is almost irrelevant. There are lava flows that will fill it. There are hydrothermal hot water explosion events. There are resurgent domes that could erupt. The Sour Creek and Mallard Lake resurgent domes, those are areas where there's 2 close fingers of magma that come up, bulge those areas up. They're more likely to go. Their size is smaller, so they would have a smaller impact than what you would see, on a Discovery Channel, program.
Okay, Rob, we have a question online.
Yes.
So there is a long-running discussion about the age of the water as it comes back to the surface in Yellowstone. Do you have any ideas or references?
Yes. The age of water is datable. What we use to do this are cosmogenic isotopes. So when a droplet of water goes through the atmosphere, it picks up these cosmogenic isotopes. And then when it goes into the subsurface, it's no longer exposed to those cosmogenic isotopes. So that's a clock that can be used. And John Sonderegger, who was at the Montana Tech for many years in the Bureau, he went around and used cosmogenic isotopic dating to date waters in Southwest Montana, and found that many of the waters coming out of warm springs and hot springs were quite old, 8,000, 9,000, 10,000 years old. So in other words, there's an ancestral supply of groundwater throughout much of Southwest Montana and probably the park as well, that is a function of the glacial period going away, and that water from glacial melt and that period of higher water, higher precipitation, which ended about 11,200 years ago. A lot of that water got into the subsurface and is working its way out now. So that when you date it at the point that it emerges, it's been underground for maybe 10,000 years.
What about the pools that are like Morning Glory Pool? They don't erupt. Is it just a big cavern?
Yeah. So the minute you say that something doesn't erupt, it's going to. There's a great example of this in Biscuit Basin. There was a group of geologists on a GSA field trip. They was led by Bob Smith at the University of Utah. Nobody knows at that time, nobody knew more about geology of Yellowstone than Bob. And he was standing there in Biscuit Basin talking about how that particular spring has never erupted. And right as he said it, it erupted. And a person took a picture of it as they were all running away from it. So it's very hard, as Hank said in the film, to predict these things because it's a plumbing system issue in the subsurface. So the key is really constriction. If you constrict the flow out, you have a better chance of getting a geyser. So if you really just want to think about it in the most simplest terms, a spring is going to have a nice open plumbing system to the surface, whereas a geyser has a complex system that has constrictions. Does that help?
You showed us pictures of the ash columns.
Yes.
Could you remind me where those are and what happened to the rest of the ash around it that made a column form?
Yes. So there it is. So that's just one particular example of an incredible exposure of these ashes, and they're all over the place. In fact, if you look at this picture, you can see them here. See them down there, the white in the distance. So they're all over the place. But there's this one spectacular spot. I don't like to give a lot of the details, but I trust a group like this. I don't know how widely this gets shared, but they're very vulnerable. And everybody and his grandmother's brothers carved their name in them. But like most love, it goes away quickly. And so the people that carve their names in the ashes think that it's going to be there for time immemorial, and 5 years later, it's gone. I love that. But features that I've known for 30 years are also gone every time I go back out there. So it's in the blacktail drainage southeast of Dillon. And it formed a pillar in this particular case because the ash, when it's deposited, it's a water deposit. It's not an airfall. And when lahars, which are water deposited ash and rock debris and so on, when they come to rest, they dewater. And because they're porous. So when they dewater, they become very sticky and hard. You know, the animals trapped in the Toutle River lahar from the Mount St. Helens eruption in 1980 and people had to be dug out. You know, they couldn't get themselves out. It was like being trapped in cement. The contraction of that drying out creates cracks. And the cracks then become avenues for vertical weathering. And you get a pillar. Okay? Correct. Yeah, what happened is there were fractures there were four fractures, right? And it created it created a square. And the weathering occurred in every fracture around that square, and it created a round pillar ultimately. And it happens pretty fast. I mean, that's a pillar that could be gone within a few years, especially if people get their hands on it. Because they do stuff like push them over. You know, we're monkeys. Question?
Going back, there was one comment and it was from earlier, Anne's earlier question. That asthenosphere is Greek for sphere of weakness.
Thank you.
In contrast to lithosphere, which is sphere of rock.
Yeah, thank you. I knew it was something to do with being mushy.
You mentioned geothermal energy, and we hear a lot about wind energy or solar energy, and
Yeah.
geothermal has been used with heat pumps, but I'm wondering if that's a whole nother topic we could go into
It
at
is.
some point.
Jeff's going to do it, and that's coming. But I'll just weigh in that, and Jeff and I were talking about it before the talk. This is a huge resource potential for humanity. Everywhere around the globe, you saw the map. There's geothermal resources, and so if you can tap it with a well, and we've got plenty of technology on how to drill deep wells, you have the potential to generate a lot of continuous energy, not when the wind blows, and not when the sun shines, all the time. So watch geothermal. It's going to be huge.
Okay, well, thank you, Rob. Thank you
You're
for
welcome.
coming over.
Thank you very much.
Thank you.